In section 5.3, we're going to look at the exponential distribution. The exponential distribution is useful when you have a situation that is not uniformly distributed, so there's not an equal likelihood for all events, but there is a higher likelihood for low numbers and a lower likelihood for high numbers. So a couple of situations that might fit this would be the length in minutes of a cell phone call. Okay, while you might occasionally spend an hour on the phone with someone, you're much more likely to spend, 5 minutes on the phone with someone. So more likely to have shorter cell phone calls than really long ones, and things like car batteries, right? So maybe you have a car battery that fails pretty frequently in the first 24 months, but then they don't tend to last as long, so it's less likely that a car battery would last 70 months or something like that. So situations where you're just more likely to have lower values than higher values will sometimes fit an exponential distribution. So the curve for an exponential looks like this. It's an exponential decay curve, if you're familiar with that from algebra or pre-calculus. And so looking at the bottom of this screen here, the f of x is me to the negative mx. Typically what will happen is we'll be given that a certain situation fits an exponential distribution with a mean of such and such. Okay, and the mean is mu, remember. Well, m is 1 over mu. So typically the mean is what's given to you, and then you find m, which is m is the decay factor. It's the exponential decay. Factor is not the right word. The decay coefficient. So you find m by just doing 1 over the mean. So you can see here on this graph that the shaded area represents a probability that x is between 4 and 5. And I'll show you in just a moment how we find probability using the exponential. It's not quite as easy as finding the area of a rectangle like we did in section 2. So in this one, the standard deviation formula is actually really easy. If you're given the mean, then you're given the standard deviation because they're the same. When we describe with notation that x is distributed as an exponential, we use this x tilde again, distributed as e with m as the parameter. Okay, m is that decay coefficient. Now the CDF function, this is what tells us our area, and the CDF function is always going to tell you the area to the left of the x value that you plug in. So the CDF function is 1 minus e to the negative mx. So it's going to be really important that you keep track of the PDF function, okay, at the bottom of this slide, me to the negative mx, and the CDF function, 1 minus e to the negative mx. Okay, they are different. The CDF function is what we will actually use to find the area, which, remember, equates to probability. The PDF function actually defines that blue curve that you see there. The PDF function is the curve. The CDF function is the area. Okay, it's important that we keep that straight. So here is example 5.7, where we have a postal clerk spending some amount of time with customers, and that amount of time follows an exponential distribution with a mean of 4 minutes. So we want to find the PDF function and sketch the curve. What we'll do is we'll use Desmos to show this curve. I think that would probably be the most effective way, better than me sketching something by hand. It's not terribly difficult to find m in this case. M is just going to be 1 over 4, or 0.25. So our PDF function will be 0.25 e to the negative 0.25 x. So let's take a look at Desmos and see what that looks like. Alright, so here we have our PDF function, 0.25 e to the negative 0.25 x. And the toughest thing about using Desmos to look at this is just trying to get your axes situated in such a way that it makes sense. Our scale for the y-axis needs to be pretty small values, right? Because our y-intercept is here at 0.25, but we need X values that take us out, for 10, 12 minutes, something like that. Remember, this situation is about minutes spent with customers. So the mean is 4 here, but that means that it makes sense that this clerk would spend between 0 and, who knows, 10, 12 minutes with customers. So if you're not sure, if you've never used Desmos before, to adjust the axes, you hit this little wrench up here, and then you can change the x-axis or the y-axis and make it fit the way you want. So here we have a pretty good picture of this PDF function. Alright, so now suppose we want to find the probability that the clerk spends less than 3 minutes with a customer. Okay, so now we're going to use our CDF function. And our CDF function is probably best just used with the calculator, where we're going to type in 1 minus E, which if you don't remember where E is, there's the LN button, which is just above the on key. You hit second LN, and it brings up E with an exponent already started for you. So 1 minus E to the negative 0.25 x. Excuse me, not x. And in place of x, we want to put 3. So we do negative 0.25 times 3, all in the exponent. If you are dealing with one of the new style calculators where it actually looks like an exponent on your calculator, then that's real easy, just negative 0.25 times x, times 3. If you have an older style calculator where all it shows you is that little caret symbol, then you'll want to put negative 0.25 times 3 in parentheses. But in any case, what you should get here is 0.5276, so let's call that 0.528 would be the probability that this clerk spends less than 3 minutes with a customer. Now, remember that the CDF function only gives you less than. So, let's see how we deal with this situation. What if we want to know the probability that the clerk spends between 3 and 5 minutes with a customer? Well, what we have to do is we have to find the probability that the clerk spends less than 3 minutes, and then again find the probability that he spends less than 5 minutes, and then we need to subtract those two values. So we've already done the 3 minutes one. So in your calculators, repeat what we did a moment ago, but change it to 5. So 1 minus E to the negative 0.25 times 5, and what you should get is 0.713 something. Okay, so now we just subtract those two. 0.713 yada 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 minus 0.5276, that was our probability for the second part of this example. And when we subtract those two values, what we get is 0.18586, so 0.186. Okay, 0.186 is the probability. So anytime you have a between, like we have here, you want to subtract the two values for those two times. All right, hopefully that makes sense. The exponential distribution has an additional property that is interesting and worth knowing. It has what we call a no memory property. And what that means is, say that you are waiting for your order at a restaurant, okay? And the times that people get orders is exponentially distributed, yada yada. So what this is saying is the probability of you waiting 10 minutes, okay, given that you have already waited 5 minutes, is no different than just the probability of you waiting 10 minutes. Okay, so if you've already been waiting for some amount of time, the probability that you will wait the next 10 minutes is exactly the same as the probability was for the first 10 minutes. That may seem non-intuitive, but it is in fact true. So, practice questions 46 to 55 is the suggested homework for this one. Again, the practice section is a little longer if you want to seek out more examples, but in particular, look out for examples that have percentiles. You may want to try a couple of those because that actually involves solving an exponential equation. So I didn't show you that in the example, but if, for example, I said, find the 60th percentile value, what you would want to do is set your CDF function equal to 0.6 and then solve for x. So little solving exponential equations in there that I didn't show you, but I think hopefully will be within your grasp. It's worked out a lot like the one that I showed you for uniform distributions in the last section, only this time you're solving an exponential equation. So let me know if you have any questions, and I hope you have a good time with this as we finish up the first half of summer stats on our way to the midterm exam.